All right. Hello, everyone. Happy afternoon and all that jazz. This thing doesn't work. So logistics. Remember, y'all's 2D kinematics is due this Saturday. The reason for that is, well, we finished it last Friday or Thursday. And yeah, we're in forces now. And just to give you all a sense of time, there's only 2 weeks left before the exam is 2 weeks from today. The first test is 2 weeks from today. So today's the 30th. Our first test is the 13th. 2 weeks. And so we're going to do forces today. We'll finish up forces next week. And then we'll have the review day on Tuesday and then the test. So nearing this point, the goal, again, the reason the 2D kinematics is the goal is that you're comfortable with 2D kinematics by kind of somewhat comfortable, not like maybe fully comfortable, but like you have a sense of kinematics, you feel like you know what you're doing. And if not, that's okay. There is some time. But again, we got this new skill set of forces coming in, and so it's just to help with pacing. If at this point, so there's a few things to point out here. I get the question of how to prepare for the exam, how to study, what should I be doing, how should I be feeling? So reminder to you all, there's the questions in the PowerPoints, the like multiple choice things. I call the top hat questions. Those are conceptual questions. So that's like a group of questions in and of itself. And then you have the problem set problems, and those are numerically answering problems. And those are their own set of things. The test is going to be a combination of the two. You will have questions that require no math, like the conceptual ones we've done in class. And then you'll have questions that involve math. They're going to generally be a ratio of about 40% conceptual, 60% numerically solving. That's kind of the ratio to expect in the test. And that's generally also, the quizzes ideally are kind of a like mini test in some ways. Like that's ideally the ratio that they express as well. About 40% conceptual, 60% solving. And that can vary from week to week. Sometimes some sections I just put more numerical because there's not enough conceptual questions I can come up with. So, great. Topic-wise, that's what to look at. Strategy-wise, how to study through these. So you can do stuff on your own. Great strategy. You can work with other people. Also great strategy. If you are not finding traction, if you are having difficulty grasping the steps, if you're having difficulty, like you're just not sure what's not working, that is when you want to go to someone. And that someone could be someone you know who's really good at physics. That could be my office hours. That could be the help room hours I posted. That could be the SARC tutoring things. That is where individual help is going to help identify where the challenge is. It could be in just the definition of the variables. It could be in the process. There's so many places it can be. But if you're not finding traction, if like you're doing these problem sets, you're like, I'm just not sure what to do. That's when you want to go to someone because they're going to be able to kind of accelerate that process a little bit. They're going to be able to help identify where that discrepancy is. And all that jazz. So if you haven't experienced it, highly recommend that. And that is something you want to do sooner than later in terms of connecting with someone, because that's not going to help you that much like a week ahead. If there's like some big problem in your study, like some big conceptual mix up or like just things aren't clicking, if you make the decision to start reaching out or start doing these things like a week in advance, it's not enough time. Physics is not one of those things that you can just cram and then it'll all make sense. This stuff takes time to settle in. It is not, it's just not something you cram study. Like it's not going to go well. This is not a memorization game. It's not like, if I just spend a bunch of time in the last 2 days, it's very rare for that to be effective. Physics is one of those things you have to spread it out. You have to work on it. You got to give your brain time to process in the background. So as time goes on, you'll see what I mean there. It's just how it is. It's one of the reasons why physics in the summer semester is absolutely brutal. There's not that time to do so. And especially if you do summer C, physics can work, but summer A or summer B, it's one of those, if you don't know the physics or don't have like individual help the entire time, it's pretty like you don't have that time for processing. But we have the time. Even if it feels tight, there is time. I mean, I say there's time, as much as I can give. Okay, so that's my little aside. In the next week or so I'll be making your all's test. That sounds like I don't know if that sounds easy or difficult. Making a good test is a challenging thing, so I'll be working on that over this next week and making it and testing it and yada, 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 double checking my work. But I'm going to send out an announcement sometime this coming week with what I'm about to tell you. The test is going to probably be 20 multiple choice and then 2 free response where you pick one out of the 2. It's going to be kinematics and forces. You do not need a Scantron. I will provide one for you. I use something called ZipGrade where I print out the Scantron. It's the last page of the test. You just kind of rip it off and it's there. It's great. So I'll provide that for you all. The only thing you need to bring on the test is that 5x8 note card. This coming week, I'll bring 5x8 note cards, blank ones, to start passing out. You can put whatever you want on that note card. You can print papers and glue it to it. It just can't be a flip book. Whatever's on it needs to be adhered to it. Otherwise, it's not a 5x8 note card. Anyway, so your 5x8 note card, if you don't have that, you'll still be fine. You technically have everything you need on the test for it. That's just additional, whatever you want. Pencil, pen. I highly recommend pencil. Using a pen on a multiple choice exam is a terrible decision because you've seen me make mistakes. You will make mistakes. Pens don't let you fix mistakes. Anyway. And then your ID and a calculator. The reason for the ID is when you turn in the test, we just check that your ID matches and all those things. Make sure you are who you say you are. And any calculator except your phone. Graphing calculator, scientific calculator, 4-function, whatever. I don't care what kind of calculator. The math is not what I'm teaching you in this class. The math just confirms your process. The math is the least interesting part of the entire process. In upper level physics courses, we just stopped using numbers entirely. It's all step 3 is the end of the problem. Step 3, hey, what's the equation that relates all these? Get the variable you want in terms of everything else, and that's the answer. So in this class, we use numbers because doing that whole thing in variables is a skill in and of itself. But yeah, it's the least interesting step in my opinion. So any questions about the test? Again, I'll send this all out in emails, but if you have a question about the test, I can almost guarantee you 10 other people do as well.
You said how many multiple choice?
20. Yeah. 20. Yeah.
Free response?
Free response, 2 free response, but pick one out of the 2. 20 multiple choice has kind of been the sweet spot I found where I want to ask as many questions as I can where you have enough time to complete them. Because the more questions I ask, the less penalty it is if you make a mistake on one of them. If I only ask 10 questions and you miss one, that would tanks your grade. But if I ask too many questions, you don't have the time to complete them all. So it's a delicate balance of giving you all the best opportunity to show what you know, but not giving you so many questions that you can't actually think through them all. So 20 is kind of the sweet spot I found.
In the syllabus, it says something about if you do both of them, the free response questions.
Yeah.
Partial credit for them.
So partial credit's always on the table, and there's the rubric there for the partial credit. If you do both free response questions, you have to pick one of them. If you don't pick one, the grader's just going to pick the first one. They will look at the other one only if it's perfect, because that's really easy to grade. Again, this is just to make grading more expedited, because normally I have a class of 300 students, and so grading 300 problems can take a bit of time. Grading 600 problems take a lot of time. So the good news is generally if you feel like you can do both problems, you're probably going to get a good grade anyway, because that means you have the time and stuff like that. Not to say that time is going to be incredibly tight, but it is a little tight. You'll have enough time. The challenge is you might not have enough time to check your work as much as you'd like, which is a bit of a bummer, but it's the constraints I exist in an hour and 20-minute class, and I haven't figured out a great solution to it. I don't do stuff online tests because I don't want to, for people, anything that's online, it's too easy to cheat, in my opinion. One of the easiest ways to cheat in an online test is just have someone else do the exam for you. And there's very minimal ways, it's so easy to get around that. Any barriers I could put up there. So that's why I do in-person stuff. I never want people with strong morals to suffer because people that don't do various cheating things. That's I don't want to penalize people for having strong morals kind of thing.
But it won't penalize you.
No, I won't penalize you at all if you do both. No harm there. All right. Any last questions?
During entire class time, right?
During entire class time, hour 20 minutes. Yeah. And generally my rule is I'll do the test myself and I will aim, this is going to sound rough, I'll aim that I can finish the test in 20 to 25 minutes. The logic there being I know how to solve every single problem. So really I'm just timing a little bit of how long it takes to write it out if you immediately know what to do. Yeah.
Is there space to write down the problems or are we going to be given scratch paper?
Both. There will be a little margin on the right side, and then I just put a blank sheet of paper attached to the test as well. And then if you need additional scratch paper, I'll have some. Yeah. It is in this room. Every single thing for this class will be in this room, including the final exam. All right. These are good questions. Edit. Yeah.
Where can we find more practice problems?
So at this point, I just have the problem sets. Generally, if you can do the entire problem set thing, you're good to go. It is, in my opinion, now you all probably have way better memories than I do. In my opinion, though, it's not something you can memorize. But again, you all have better memories. You might be able to memorize them all. But if you've gotten to the point where you can memorize all of them, you've done them all in detail, you very likely know what you're doing. It's very rare for me to encounter a situation where someone has done the entire problem set, themselves and things like that, and they know how to do it, and then they do poorly. Those things generally do not happen. The only way that happens is if, when they solve the problems, someone else kind of had to work with them through every single one. You want to be able to look at a problem and say, you're going to know you're ready when you can look at a problem, read it, maybe think about it a bit and say, yep, I know what I'm doing. Before you even start writing stuff down, you kind of have a sense of the direction to go. That's a really good sign. If you need to work it out, that's fine. There's no problem with that. But that is kind of when you know you're in a good place, when you can look at a problem, and not because you've seen that problem, but because you're like, okay, given I see this information, yada, yada. Something I'll release as I get closer is I'll take the problem set and I'll mix it all up, because right now it's organized by topic. When I mix it all up, and you can do that yourself, just copy and paste things, but I'll do it sometime in the next week. One of the strategies, can you figure out what type of problem is it? Is it kinematics? Is it forces? Yada, yada. Right now it's all nicely organized, so it's kind of easy to figure that out. When you mix it up, that's what's going to look like the test. And I'll try to do the same thing I'll definitely do it for that. Time pending, I'll try to do it for the top hat questions as well. All right. So any more questions, shoot me an email. I'll send out an email with all the logistics of the test. But at any point, if there's like common questions, those are good for me to know, so then I can send out announcements and all that jazz. So last class, forces, Newton's laws. So many interesting things. We got through Newton's first and second law. First law, things keep doing what they're doing. Object in motion remains in motion. Object at rest remains at rest. Things keep doing what they're doing until a force acts on it. Just because something is moving doesn't mean a force is acting on it. An asteroid flies through space. Nothing is yanking it around. Nothing is moving it. It will keep flying forever and ever and ever until something affects it. Then second law, F equals ma. So we talked about that one, though I didn't highlight the answers for some weird reason. What's hard to move on Earth? A small car or big truck? The big truck. What's hard to move in space? Also the big truck. It was about mass, not about weight. And so Isaac Newton discovered F equals ma. And in my opinion, the more interesting one was A equals F over m. Because acceleration is really the thing that actually is meaningful. Acceleration tells you whether you speed up or slow down. You find that by doing the net force divided by mass. Great. The unit for force is newtons. Mass is kilograms. Acceleration ms squared. There's mass. And then we did a problem on it. Kinematics and forces together. They go hand in hand because remember, kinematics is describing the motion. Forces is saying, why is there motion in the first place? Why did that thing even start accelerating? That's the link between the two. All right. How much is a Newton? So I think I already mentioned this one, but just to remind you all, there's the mass, there's the acceleration. So F equals ma. So if you do the math, 0.5 times 9.8 equals a force of negative 4.9 newtons. That just gives you a sense of how much a Newton is. If if you've held a baseball, how much a baseball feels like is about 5 newtons downwards. That's the only reason for that. All right. This question. This is a classic. Anytime you ever take, this question is such a classic question in physics. A truck hits a fly. Which experiences a greater force? The truck, the fly, or the force is the same? There is only one right answer. All right, if you haven't guessed yet, give it a guess. We'll go like 20 more seconds. In 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. All right. No one ever likes this answer. They're the same. No one likes that answer. All right. And so don't worry. I'm going to make it match your expectations. Yes, the fly dies. We all know that. The fly dies, the truck's fine. That is a known thing. And this is where I have to convince you all it's the acceleration that matters, not the force. It's the acceleration that matters, not the force. How much something accelerates, that's what determines what's going to happen to it. They're going to experience the same force. This force is not going to be that big. This force is really not going to be that big. I don't know what it's going to be. We'd have to actually have more numbers here. But let's just pretend like it's 1 Newton. If you push a truck with 1 Newton, not that much is going to happen to it. But in the case of a fly, a lot more is going to happen to it. So, for now, let's just say that they're the same. So it's Newton's third law. For every force, there's an equal and opposite. But let me show you all, let me connect it to what you expected to happen. So again, I expect this answer to be vastly different. Yeah, no one likes this answer. This is one of those things I mentioned that I understand reality. You know what's going to happen here. And so my goal is to connect your understanding is not about forces. Your understanding is about acceleration. You've seen a fly die. Because the acceleration, not because of the force caused the acceleration. So, Newton's second law, F equals ma. So I'm just going to replace these. I'm going to replace force with acceleration. Now, I gave you the mass of the truck. So that's going to be, let's call the truck object 1 and the fly object 2. So the mass of the truck is 2,000 kilograms. That's already in base units. I didn't give you the mass of the fly. But it is 0.00, I think 5 grams is what someone found. Let's say it's even bigger than we might think. A fly doesn't weigh much. You know that. We need to convert that to kilograms. So I need to move that 1, 2, 3 times. I always have to count it myself, as funky as that sounds. 1, 2, 3. Great. This is why I generally just chuck the e to the minus whatever. Great. There's the comparison of masses. Now let's plug those in and see how the accelerations compare. This is where it's all going to match your expectations. 2,000 times the acceleration that the truck is going to experience equals 0.00005. Double check all my zeros. Times the acceleration of the fly. So the acceleration of the fly, if we solve for that, is going to be 2,000 divided by 0.0005, and that's going to be the comparison between it and the truck. So let's plug this in. 2,000 divided by this tiny, tiny number. 2,000 divided by 0.00005. And we get that the fly experiences an acceleration that is 4 followed by 7 zeros. 1, 2, 3, 4, 5, 6, 7. 40 million times larger than that of the truck. So this matches what you expected. The fly accelerates 40 million times more than the truck. The truck doesn't really accelerate at all. The fly accelerates a lot, and that kills it. The fly's velocity goes from 0 to 60 miles per hour in an instant of a second, and that absolutely kills it. The truck goes from 60 miles per hour to 59.9999999. It barely changes at all. So it's acceleration that matters, not force. And so this statement, though, that the forces are the same, this whole thing is just to make you feel more comfortable with that statement. Anytime you've seen two things collide each other and one gets affected and one doesn't, yeah, you did notice that one accelerated and maybe one didn't accelerate as much. That's what you saw. You can't see forces. You can't see a force acting on something. You can only see whether or not something's position is changing and how that's happening. Anything you all observe in reality is just position-based. An object went from this location to this location. You can't see a force. You can only see the consequence of a force. So anywho, that's a big mindset shift. You've used force a lot in life. You're like, oh, I can see force. You can only see the consequence of it. Anywho, Newton's third law, for every force there's an equal and opposite. Every single force. Right now, the earth is pulling you down. You are pulling the earth upwards just as much as it's pulling you down. But you're not affecting the earth because its mass is absolutely ridiculous compared to you. So you don't really cause the earth to accelerate at all. Whereas you do accelerate if you jump off something or stuff like that. Right now, every single one of you is sitting in a chair. Gravity's pulling you down into the chair. You're pushing into the chair. The chair is pushing back with the exact same force. If you punch someone in the face or punch a wall, the wall punches back. That's why your hand hurts. Any object you push, you feel it because it pushes back on your hand. Otherwise, if it ever pushed back on you, you wouldn't know you're touching it. There wouldn't be any feeling to that. When you jump, you aren't pushing up. No one jumps by, I guess you could try to throw your leg upwards in the air. No one jumps that way. No one jumps by throwing their legs upward. When you jump, you push down, which is an interesting thing to think about. So why do you go up? Because the ground pushes you up. Every single force, every single interaction between objects, it doesn't matter how big they are. When you push on the earth's much bigger than you. Doesn't matter. If you push on the earth, it pushes back the same. Every single force is equal and opposite. The moon pulls on the earth the exact same as the earth pulls on the moon. And any possible interaction you can think about, equal and opposite. Another good example of this is pushing on a wall. When I push on a wall, the wall pushes back on me. You might not see that because there's another force. Okay, great. I'm pushing on the wall is pushing back. Why aren't I sliding backwards? What's pushing me forwards? Friction. My feet are pushing into the ground right now, and the ground is pushing me back against it. Easy way to prove that, get rid of friction. I take my shoes off and I push on the wall, and now I start to slide backwards. I'm not pushing myself backwards. The wall was pushing me backwards. The reason I wasn't moving before is there was another force acting on me, opposing that and any of that. So this is why this stuff is so interesting. Again, you all have seen lots of things pushing on each other. And football is one of those classic examples. People get tackled, the bigger person often wins, but they're both pushing on each other the same. If two people run into each other helmet to helmet, they both have the chance of suffering concussion because they're both going to experience a force. Now, one person might move more because either the ground, they don't have as good a footing, so there's not that opposite force holding them up as much, just like that example of me pushing in this, or their mass might be smaller, so it's easier to accelerate them, all those things. But yeah, it's just one of those, it's subtle, but man, does it make it changes the way you think about things. And now anytime you go anywhere, when your car drives forward, your wheels are pushing on the ground backwards, and then the floor is pushing your car forwards. Nothing in your car pushes your car forwards. The ground is pushing your car forwards. But you have to push back on the ground to make that happen. Yeah, so many things you can think about. Every time you all walk, when you change direction, if I want to go to the left, I don't push myself to the left. I don't there's no way to push myself to the left. I can't shove my shoulder and make myself go to the left. You push on the ground to the right, and that pushes you to the left. So many fun things to think about. And it's subtle. So now that we've talked about that, just to see how much that landed. Truck runs into a fly, which experience a greater acceleration? The truck, the fly, or the acceleration is the same. All right, we'll go like 10 more seconds. In 5, 4, 3, 2, 1. Which one's velocity changes a lot? The fly's. The fly's velocity changes a lot. The truck, you don't notice. Your speedometer doesn't change when you hit a fly. So, the force is the same, but the acceleration is different. And that's what you're accustomed to seeing. All right, great. Those are Newton's 3 laws. I'm not going to ask you any questions on the test like, which of these is Newton? Here's a scenario. I punch the wall punches back. Which of Newton's laws explains that? No, I don't care if you know which law is which. I do care that if I tell you I hit a wall with 10 newtons, how much does the wall hit back? 10 newtons. I care about those kind of questions. I care about, do you understand it, not the memorization of which law is which. The ideas behind them is what's important. Yeah.
Is there ever any like negative or?
Yeah, that's a great question. There is a negative. These are vectors. So yeah, if I punch the wall, I guess the better one would be if I punch the wall to the right, if I put a force of 10 newtons, positive 10 newtons, it will push back with negative 10 newtons. So we're about to draw some free body diagrams where we draw an object and we draw all the forces acting on it as arrows. If you drew a free body diagram of the entire universe, all the forces cancel out. Every force to the right has an equal and opposite to the left. Every force up has an equal and opposite down. Yeah, it's a great question. And down is negative, to the left is negative, just like all the other vectors we've done. All right, so speaking of free body diagrams, this slide, so this one's a circle. I tend to draw them as squares. I don't really care how you draw your objects, but basically you just want something that's your object. A square is easy to draw. A circle is easy to draw. So we're going to draw free body diagrams. I don't care. This box is a person, a car, a plane, anything you want it to be. You don't need to actually, when I say draw a free body diagram of a person, I don't need you to draw a person. Like that actually it covers arrows and things. A box, circle, that's the way to go. Fantastic. That's, it's the whole spherical cow situation. We don't really care what it looks like. So what the object looks like. So this one is an example. Great. You got a dog thing getting pulled in 5 different directions. I'm not going to ask you to draw a picture that looks like it's not a dog. What is that thing? Bear? Yeah, bear. I'm not going to say on the test, you don't need to draw a little bear and draw the arrows. If you want to, you can, but that takes time. And I don't know. It's just, sure, if you want to, if it makes you happy, go for it. But for the sake of convenience, there's the bear. And then you just draw the arrows. Which way a force is a push or a pull. When you're drawing these, the question is, which way is it getting pushed or pulled? And every single push or pull gets its own arrow. So a dog is pulling it up to the right. So we draw an arrow there. All arrows start at the center of that object. We draw them all from the center. So that one's up to the right. Another dog's pulling it up. Another dog's pulling it to the left. Another dog's pulling it down to the left. Another one's pulling it down to the right. Free body diagram. You just draw all the pushes and pulls acting on an object. This skill is absolutely critical to solving any force problem, because if you can't draw all the forces, then you can't include them in your math, and it's all going to go south from there. Also, the direction of these matters, like someone asked, is there positive and negative? Yes, if you draw a force to the right, it's positive. If you draw it down, it's negative. The direction of these matters this picture is going to make your life so much easier. And if you try solving force problems without drawing a picture, that just sounds miserable. Like this is not a beginner skill. This is a expert skill. This is a skill every single physicist does when drawing the forces acting on something. Because if you don't do it, you're going to make a mistake. Like the chance is just so high. It's just critical. Drawing the picture, this is absolutely critical. So this first problem is just practicing this. The telephone pole has 3 cables pulling on it. Here's my telephone pole. Woohoo. The first force is 300I plus 500J. The second force is negative 200I, and the third force is negative 800J. We're going to find the net force and find the magnitude and direction of this force. So this problem is just saying, hey, can you draw vectors? Sure, it's forces, but it's the same skills you've been working on. Now it's just in units of newtons. So I'll give you all like a minute to draw the picture of that, and then we'll kind of I'll go through and solve it. But I could have given you all this problem in week 1, honestly. Like, there's nothing new here outside of vector stuff. All right, so we're going to draw some arrows. I'll color code them. We'll make F1 red, we'll make F2 green, and F3 will be blue, just to make it easier to spot what's what. All right, so F1 is going to be, remember, we always start here in the middle, so we're going to go 300 to the right. You get to decide how big 300 is, but then after that, everything is measured with respect to that. So this is 300, and then I'm going to go 500 up. 500 is bigger than 300, so I'm going to make it a little bit better. The more to scale your picture is, the easier it is to determine what the right answer is going to be. The better sense you have of what's going to happen. Now, in some problems, you're not going to actually know how big these arrows are to begin with, so you just got to pick a size and stick it there. But if you can make the arrows more accurate, it is ideal. All right, great. That's arrow 1, 300 to the right. 500 up. Force 2 is negative 200 to the left, so it's a little smaller. So there's F2. And then F3 is going to be straight down 800. And so the free body diagram here, to actually simplify things a bit, so like I made that whole right triangle. The free body diagram, this is really the free body diagram. The 2 sides just helped us draw that one, but there's our 3 arrows. F1 points up to the right, F2 points to the left, F3 points straight down. Great. The givens are F1, F2, and F3. So F1 equals 300 I hat plus 500 J hat newtons. F2 equals negative 200 I hat newtons. F3 is negative 800 J hat newtons. Find the net force. Anytime you all see the word net force, so F net, that always means add up all the forces. So net means add. Net means sum. Find the sum of all the forces. And I think I mentioned this last time. This is the Greek letter sigma. It means add them all up. Now, these are vectors, so remember we have to do it in the x and the y. That doesn't go away. They're vectors. You have to do this. There is no getting around it. Something that's kind of interesting here. Your phone has your phone has so many sensors in it. One of them is it actually has accelerometers that measure acceleration. It has 3 of them. One for the x direction, one for the y direction, and one for the z direction. Your phone also has magnetic field sensors in it. One for the x direction, one for the y direction, one for the z direction. There's lots of, it also has gyroscope rotation, also 3 different gyroscopes. So if you want to measure these things, like even when you take measurements, you have to do all 3 dimensions. That's just how it works. There's no getting around it. All right. So then we do it. We just sum them up. There's not really, sum up the forces. So in the x direction, to clarify that, and I guess I could write this out a little bit more. So the sum of forces in x is going to be F1x plus F2x plus F3x. The sum of forces in the y is going to be F1y plus F2y plus F3y. In this specific problem, they don't all have x and y components. So if they don't, it's just 0. But I'm writing that out explicitly because that is what ultimately you're doing. If it doesn't have one, then the value of it's 0. So let's show that here. If we're working in the x direction, the sum of forces in the x is going to equal the x component of 1, which is 300, plus the x component of 2, which is negative 200, plus the x component of 3, which is 0. You don't, on your paper, technically have to write that plus 0. I am just writing it explicitly to show you that that is what's going on. So that equals 100 newtons. Then we're going to do it in the y direction. Sum of forces in the y is going to equal the 500 from force 1, 0 for the second one, and then negative 800. The reason I write this all, I always write it as all plus, 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 plus. Then if it's down, I just put it as plus and negative. Yes, that is the same as subtracting, but for me as a teacher, this gets around having to explain when do you add and when do you subtract. Just always add, and if it's down, it's negative. Add a negative. Gets around some of that questions of that. So if you'd prefer to do 500 minus 800, it's the same thing. But I think it just makes it a little bit more clear what I'm doing when I just say it's add. And it aligns with the whole F net is the sum and all that good stuff. Okay, so great. Those are my 2. This question did just say find it in the component form. Now the answer here is not in component form. The answer here is the magnitude. So then you gotta, just to, as an extra fun thing, remind you all, how do you do that? You got the x component, you got the y component. So I'll do that on the next slide. I'll copy those over. And we'll do that last little bit, but it's just vector stuff. So great, I can draw this if I want. Sure, let's make it red. So F net's going to be 100 to the right and 300 down. So my net force, the magnitude of it's going to be down to the right. And if we look at our picture, that matches. F3 is going to win in the up and down direction. And F1, it turns out, wins in the left-right direction. So F net X and F net Y. So to find the magnitude of F net, square roots of 100 squared plus 300 squared. Technically, it's negative 300 squared, but the negative is going to go away anyway. So when I write these out, I just don't even bother with it. Because honestly, when you put that negative, you might accidentally forget to put the parentheses around it. And then when you square it, that can result in mistakes. So in my opinion, when you do this, it's actually better just to, the negative is going to go away. It makes it less likely you'll accidentally forget those parentheses in your calculator. I find it results in less mistakes for me. So that's why I'm not putting the negative in this thing, is it actually results in less mistakes. 316.23 newtons. Great. That's my force. The angle. So remember, the angle is pretty much always defined with respect to the positive x-axis. So in this case, we're below the x-axis. So theta is going to equal tangent inverse of F net y over F net x. I'll let you go through if you're like, where did that come from? Opposite over hypotenuse. Sorry, opposite over adjacent. So here I put the numbers in as positive. That's my personal preference. And then I decide whether it's positive or negative and all that jazz after. So you get 71.565 degrees, and that is below the x-axis, the positive x-axis. That is one way to write the answer. Or you could say it's negative 71.565 degrees and leave it as is. And then the assumption is with respect to the x-axis. So, vector stuff. There is nothing honestly new in this thing here. Yeah?
Can you repeat why you said you knew like that's the angle it was asking for?
Yeah, so whenever it says direction, there is technically... So when I mention angle, it's like me saying, how far away is this water bottle? I can measure that with respect to many different things. I can measure where my water bottle is with respect to the right side of the desk, the front of the desk, the back of the desk. In angles, the convention is the positive x-axis is our kind of zero. Now, if this is a free response, as long as it's clear where that angle is, I'm good. If you told me so in this case, if you told me 18.44 degrees to the right of the negative x-axis, that's actually the same exact angle. So if it's not specified, if just an angle is given, the assumption is that's measured with respect to the positive x-axis. That's the assumption. But you could make your own statements. Like that's what I did here. I said below the positive x-axis, and I put it as a positive. That works. If you just put it as the negative, then the assumption is, okay, I'm measuring with respect to the x-axis that's below that. And that comes from the unit circle. Unit circle, the angle is measured. When you go counterclockwise, it's a positive angle. When you go clockwise, it's a negative angle. Yeah.
For the exam, so are we supposed to put always 3 decimals?
2 or 3. 2 or 3. 1 to 2% is the rule. If you're within 1 to 2% of the answer, we're good. Because at the end of the day, the only purpose of the answer is to show whether or not you did the process correctly. There will never be any answers on the multiple choice. There won't be ones that are like 1.2 and then another choice is 1.3. They'll be significantly different from each other. More than 10 to 20% different from each other. And that'd be like the closest, and that's even pretty tight. So great. Adding forces together. It's something we're going to have to do. So that was just a reminder there. Now in this is just to prepare us for the next slideshow, and you're going to see it again on the next slideshow. The next one is I'm going to teach you how to find various forces, how to actually calculate them. Because you're going to draw arrows, and then you got to calculate how big those arrows are, and then do math. So we're going to learn how to calculate the gravitational/weight force. Weight force is just gravitational force. Normal force, friction force, tension force. Those will be basically the 4 we'll talk about in the next slide. Fun fact, only 2 of these have equations. And the rest are kind of got, yeah, you'll see what I mean. So there's actually not many equations. If you all have looked at their formula sheet, there's only 2 more equations I have to teach you. And they're both really simple in form. So, anywho, we'll do that in a second. Before that, I want to do a problem to kind of prepare us as well. So this problem is kind of a preview. I haven't necessarily taught you the skills for this, but at the same time, you somewhat have the skills for this. A body of mass 2 kilograms is pushed upwards by a 25 Newton vertical force. What is its acceleration? First step, the second you see anything about the word force, draw a free body diagram. There's your body. I want you to draw the arrows. What is pushing/pulling it? Try drawing those arrows yourself. You all know enough to be able to draw this. And I say that not as like if you don't get it, how dare you. I say that like you are capable. You have enough background knowledge to do this, to draw the arrows. Oh, and assume every single problem is on Earth unless stated otherwise. Because your entire life will be on... Okay, I assume that. The vast majority of humans' lives have all been on Earth. That could change, but as of now, that's a pretty reasonable assumption to make. Maybe in 100 years that'll change. I don't know. All right, y'all tell me what's pushing and pulling this thing. What arrows should I draw? Give me one at a time. Yeah. Gravity's pulling it down. So that's one that's not labeled on the problem, but that's basically the one that's going to show up in almost every single problem you ever do, because every single problem is going to be on Earth. So there is a force, and we're going to label these, and they're all going to, I'll try to stick to this notation. I like to use F for force, and then you put a little subscript for what the force is. In this case, gravity, Fg. Note that this is not F with a G next to it, because I don't want you to multiply force times gravity. If you write it that way, you might accidentally multiply them. This is F subscript G. It's an adjective. It's the gravitational force. All right, great. Anything else pushing it or pulling it?
The 25 newtons.
The 25 newtons. Which way is that pushing it?
Upwards.
We draw an arrow upwards. Now, I don't have enough information to compare these arrows yet. That's why I told you all you're not always going to know how big to make the arrows. We're going to learn that let's just say it now. Applied force basically is anything that doesn't fit into these four categories. Anything where something's getting pushed or pulled by something, we just call it applied force. That's just kind of a catch-all for any kind of push or pull that's not due to a rope or gravity or friction or the surface. And that's 25 newtons. Great. Now we can write down our givens. Our mass is 2 kilograms. Our applied force is 25 newtons. Our gravitational force, I kind of chuck this into the givens because it's something that you can pretty much always calculate. And you're like, but you haven't taught us to calculate it. Yes and no. I think it might have shown up somewhere in here actually, but that's okay if you missed it. What's Newton's second law? F equals ma. What's the value of A for gravity? 9.8. Ta-da! You all have the equation for the force of gravity. It's m times g. Gravity is an acceleration. So just replace A with G and you all now come up with the equation for the force of gravity. So force of gravity is going to be M times G, which is going to be 2. Now and this is where a preference thing's going to sit in. The question always comes in, do I put positive 9.8 or negative 9.8? When I calculate my forces, I like to calculate them all as positive. And then when I add them together, I'll decide which ones are positive and negative based on my picture. So that's my personal preference. So I'm going to put a positive 9.8 here. And later on, when we add these forces together, I will call this one negative because the picture says it's down. So that's my personal preference. If you'd prefer, you could put this as negative 9.8 and then it's a negative force. And when you add it, great. That'll all work out. The reason I prefer to do the negatives later is it generally results in less mistakes. When you do it based on the picture, deciding, oh, this one's up, so it's positive, this one's down, that's negative, it just results in a little bit extra thinking, which generally results in less mistakes. That's been my experience. So this is why you're seeing me, because the question is, do I make it positive or negative? Just make every single force positive, and then when you add them together, right is positive, left is negative. Up is positive, down is negative. It's a nice, simple rule that we've been following, so you get to stick to the rules you know, as opposed to having to come up with new ones. All right. Great. We're solving for acceleration. Oh, I didn't do the math here. 19.6 newtons. Okay. Acceleration equals question mark. Anytime forces are mentioned, you're always going to set up these problems the same way. You're always going to be using the same equation, Newton's second law. Like that's always going to get used. F net equals ma. That is always the equation you're going to use in every single force problem. You don't even have to make a decision on what equation. It's always going to be that one. If it's a force problem, F net equals ma. Now, we're not technically going to have to do this in this problem, but just to make this, I think this is good to mention. Remember, it's always in components. You're always working in components, even when it doesn't seem like it. So even though it's like, why is he doing this extra work? The X direction doesn't matter. There is no X things. But just to get us in that mindset that X and Y exist and that we do have to consider both. I'll mention it here. So then we go ahead and start solving. So I'm going to do the X component first because it's really easy. So my sum of forces in the X. Remember this F net means sum up the forces in the X. There are no forces in the X. It's 0. So, what's my acceleration in the X direction? It's 0, which is pretty obvious. Like, do you need to do this math to prove that? No. But I just want to point that secretly you're doing this math. There is no acceleration in the x direction, in the left-right direction. Nothing is pushing or pulling it that way. Things only accelerate if there's a net force. When you push the gas in your car, you are only going to get faster if you overcome the force due to air resistance. When you're going at a constant speed, you're still putting a force forwards, but the force of air resistance is canceling that out, and your acceleration is 0. All right, so that's that little aside. In the y direction, we do have forces. So the way we're going to write this, and I'll actually write it out over here, we're going to sum up our forces. And so FA plus negative FG is going to equal MAY. I added them. Remember, the word net means sum them up. And this is where I decide to put my negative in. Why did I put it as negative? Gravity is down. The arrow is down. They're fighting each other. The applied force is upwards. Gravity is downwards. They're not helping each other. They're pushing and pulling in opposite directions. And we decide to make up a positive and the other one negative. So, now when we plug in those numbers, the applied force is 25. My gravitational force is negative 19.6. Again, I just leave it as plus. Yes, it is technically 25 minus 19.6. But I think conceptually it makes more sense when you just always add them. Whatever, it ends up being the same thing. Equals my mass times my acceleration in the y direction, and you just solve for the acceleration. This is basically what we're going to be doing for most of the problems moving forward. Draw a free body diagram. Add up all your force in the x direction, they equal max. Add up all your force in the y direction, they equal may. Yeah.
So your answer is straight up in meters per second square, or is it gonna be like kilometers per second square since the mass is kilograms?
Yeah, that's a great question. So the answer is going to be in meters per second squared. So let me just write out this one. So this is going to be 5.4 equals 2 AY. So we're going to find out AY is 2.7 meters per second squared. Acceleration always has the units of meters per second squared. Now, if you're like, but these are units of newtons. So force is units of newtons, and I'm dividing by mass. It turns out newtons divided by kilograms is the units of meters per second squared. It ends up that way. Another way to see that is technically the units for newtons are kilograms times meters per second squared. It comes from force equals mass times acceleration. They're the same units. The units for mass is kilograms, the unit for acceleration meter per second squared. So when you plug that in, the kilograms cancel. Yeah. So this is a beautiful thing about units. Anytime you find acceleration, it's meters per second squared. Anytime you have force, it's newtons. Every time you have velocity, it's meters per second. They're always the same units. Yeah. Okay, I'll leave. If you have a question at any point, let me know. Because I always appreciate when people ask questions. Because if nothing else, it slows me down for a bit, which is generally a good thing. Is this acceleration positive or negative? Not a trick question. Just the answer there. It's positive. Which way is this thing going to accelerate? Up or down? Like, is it going to... Yeah, which way is it going to accelerate? Up or down? Up. There you go. Now, one thing I do want to point out, just because it's a positive acceleration, that doesn't mean you're moving up. Now, in this problem, they do say you're moving upwards, so you are. But remember, y'all, gravity. The acceleration to gravity is negative 9.8. That doesn't tell you which way my baseball is moving. It always experiences an acceleration of negative 9.8 on the way up, at the highest point, on the way down. Do not mix up acceleration and velocity. It's one of the most common mistakes that happens in physics. Velocity is how fast you're moving and in which direction. Acceleration only tells you how my velocity is changing. And whether or not that's speeding up or slowing down depends upon the velocity. Depends on which way you're going. In this case, we're speeding up because we're moving up and we're accelerating up. But if this problem was instead moving down, this would mean they're slowing down. So, little things that get mixed up all the time. So, this is what we're going to be doing for the next week, is doing problems like this. So, we'll jump into the next one. This is where we're going to spend a decent amount of time. Largely, it's pretty straightforward. In my opinion, there's only two problems that are a little, have some nuance to them, and that's inclined planes and pulley problems. But the rest of this, in my opinion, is a fairly straightforward F net equals ma. So, we're going to jump into that. Great. So, we're going to identify different types of forces. I already mentioned them before, but you'll see them again. We're going to draw free body diagrams. And then we're going to find the net force and then divide that by mass to get the acceleration. That's the name of the game. Because acceleration is ultimately what actually matters. The whole point is to find acceleration. That's the reason we do these problems. Then if we know acceleration, we can do kinematics problems, which we love with all our heart. Okay. So, yeah, free body diagrams, vectors, F equals ma. The stuff from the last slide, basically don't forget. And as I said, it's all about learning how to find them. Add them, set them equal to m times a. That's the name of the game. It's all about acceleration and finding it. Okay, this is a big old list of forces. Really, we only care about 4 of them in here. So applied force, remember, is a catch-all for anything that doesn't fall into the rest of them. That's basically applied force. If I push this desk, that's an applied force. You push a lawnmower, that's an applied force. I pull this desk. If anyone pushes or pulls something, that's that. Gravitational force, normal force. We'll learn about the normal force. That one might be a new phrase for you. Tension. That one's going to be really straightforward. If there's a rope or a rope-like object and it's pulling something, that's tension. Tension is the force in any rope-like object. That's the best way I can describe the category of things that look like ropes. I don't know. Chains, ropes, string, rope-like things. Spring force is springs. We're not going to we'll talk about it, but I don't really have too many problems with that. Friction is going to be a big one. Drag is the force due to air resistance, and I'm only going to mention it to show you how unpleasant the equation is, and then we won't use it. So that one's really easy. And then centripetal, we're actually not going to cover until the end of the semester. And that's circular motion. And that's its own. It is F net equals ma, but instead of left, right, and up, down, it's away from the center of a circle or towards the center of a circle. So, anywho, there's the beautiful picture from before, all our forces. Remember, tension is the strings. Friction is what you think it is. Gravity is what you think it is. Normal force is maybe the only kind of new term. Normal force is away from any surface. Don't worry, there's a whole slide on it. We're going to spend a decent amount of time, either today or Tuesday, talking about it. Great. One of the first things I want to make certain we're okay with is drawing pictures. Don't worry, there's going to be slides dedicated to each of these forces. So if you're I didn't get involved, there's slides for each of these. This is just a quick overview. All right. Which of the following is the correct free body diagram for you sitting in your chair right now, as far as it looks like everyone is sitting? So it applies to you. What are all the things, whenever you do this, you are just drawing all the things that are pushing and pulling you. And I have no idea where my thing went. Did the question get sent out? Yeah. Okay, well, it's gone. Odd. It's back again. All right, so I don't know what happened there. But there you go. The key is not to pick the right picture. The key is to draw your own picture and then see which of these matches your picture. Do not start from the answers and try to figure out which one's right. Draw your own and see which one matches that. Very odd. I guess this is showing, what is this? I don't want that. We'll just, nope. Just hide that. It's gone. All right, 10 or more. It's about 10 seconds. In 5, 4, 3, 2, 1. There's, I guess end works. Sadly, it doesn't let me mark which one's correct, but I'll show you all which one's correct. So I sadly can't see what you all put, which is sad for me because I want to see that information, but here we are. All right, there's you. Remember, everyone's a box. Everything's a box. And you say, which things are pushing and pulling you right now? That's when you draw. You just say, what's pushing or pulling? So you all tell me, what's pushing or pulling on you right now? Gravity, great. Again, that's always the freebie. Almost guarantee. I say almost a guarantee. Every problem's on Earth, unless stated otherwise. It's there. All right. Now, if we leave this as is, you all should be accelerating downwards. If I leave this picture as is, you should be accelerating downwards because the only force is downwards, and the direction of the net force is the direction of acceleration. None of you are accelerating downwards. So what do we need to add to this? The chair is pushing up. We're going to learn that's called the normal force. The normal force is the force any surface that you interact with. Floor, wall. If you're touching it, if you're leaning against the wall, it pushes against you. If you're sitting on something, it's pushing back up on you. You're standing on something, it's pushing back on you. Every object on the desk is getting pushed up. There you go. There's the answer. I didn't label the arrows in these answers because I didn't want to give away too much. But in general, you should label your arrows. Otherwise, you're going to lose track of what's what. All right, great. This next problem I'm about to show you, I asked for my Physics 1 for engineering class, and 20% of students got it right on the test. So that was a question I gave some points to because clearly I didn't prepare people enough. So this is me now trying to do a better job preparing. But I mentioned that this problem is not a tricky problem. But there is, hey, where is this object? So let's see the problem. Which of the following is the correct free body diagram for a baseball in the air when it's traveling directly to the right? Do not ignore air resistance. So, draw the thing and then draw all the things pushing or pulling it at that exact moment in time. At only that moment in time. When you draw free body diagrams, it is for that moment in time because as time changes, forces change. At this instant, draw it and draw all the forces acting on it. So here's the baseball, it's in the air. So when it's up here in the air, traveling to the right, draw all the forces acting on it. Oh, I gotta send it to you. But again, draw it for yourself. Do not look at the answers here and say which one is right, because you are very likely going to make a mistake if you do that. Draw it yourself and then look at the answers and say which one matches. All right, we'll go like 20 more seconds. All right, in 5 more seconds. 5, 4, 3, 2, 1. All right. So again, we're going to draw this. There it is. It's in the air. All right. What is pushing or pulling it when it's in the air? What's the freebie? Gravity. Great. What else is affecting it? Air resistance. Which way is that going to push? Yeah, so it's going to push opposite, like you've experienced. Air resistance pushes the opposite direction to the left. Is there anything else? And so I tend to label air resistance as a friction, which is kind of might sound a little weird. Air resistance and friction, they're both things that slow each other down due to collisions with particles. If you really want, call it F air. You could call it F air, but I tend to call it as a friction force. And just to kind of catch you here, this is the answer. And I'm going to look at the responses, and I'm expecting a good amount of D's. Yep. The question is, when it's in the air, is there anything pushing it? When it's traveling through the air, there is nothing pushing it to the right. Remember, y'all, if there is no air resistance, the acceleration in the horizontal direction is 0 from kinematics. Nothing is making this thing speed up or slow down to, nothing is making it speed up to the right. There is nothing pushing it in the air to the right. Yes, I had to throw the thing to make it move. But I didn't ask you when it was in my hand. I said after it left my hand, when it's in the air. Anytime you all draw a free body diagram, it's at a specific moment in time. If I say there's a force acting on it to the right, then we're saying my hand is still pushing it up here, and that's not the case. That would mean that objects in the air would be getting faster and faster and faster and faster forever and ever and ever. So don't worry. You matched this is why I asked this question. Because if I gave this question on a test, about 20% of people would get it right. As is, but now we've seen it. So this is a really important thing to remember. At a moment in time is when we care about. It depends on where you're looking at it. So there you go. These next two I'm not going to open. I'm just going to give you the answers, and you can try them on your own. You can hide all my writing and see them for yourself. So which is the correct free body diagram for a baseball traveling directly to the right on the moon above ground? I can't say in the air in this case because there is none. So great. There's my baseball. On the moon, there is still gravity, but there is no air. So that's my answer. So again, these are good ones to practice on your own. On the moon, there's no air resistance, so I didn't even specify it, but that's generally something most people know. Great. And then this one, for some reason, my answer A, that disappears. Which of the following is the correct free body diagram for an asteroid traveling to the right, far away from any planets or stars? So you just got an asteroid flying through space. And the correct answer is C. There's no Earth or moon to pull it. There's no gravity affecting the thing. It is not going to... What is an asteroid going to do in space? It's going to go forever and ever and ever and ever. It's not going to speed up. It's not going to slow down. It's not going to accelerate because no forces are acting on it until it gets close enough to a star or a planet, and that starts to pull it in. And if it hits the Earth's atmosphere, then air resistance comes in and, all that stuff. So these are good ones to kind of work through. Try on your own. If you want more of them, ask ChatGPT or come to my office hours. I'll make up a million of these. So there you go. All right. Now I want to try to get through gravitational force and at least start touching on normal force today so that I'm at pace with my other class. We might be a slide or two behind, but gravitational force, so easy. We were at M times G, always. Done. Super easy. There's no tricks here. It's always down. This is the easiest force to calculate. That's why pretty much it just goes in the givens. Yeah.
Just to clarify.
Yeah.
Always converted to kilograms.
Always converted to kilograms. Great point. Mass is always in kilograms. The base unit for mass is kilograms. If you try to plug grams in here, you will get an answer that's off by 1,000. So very, very important thing. Why is kilograms the base unit and grams isn't? I have no idea. There's a history behind it. Someone decided at some point, and I just convey that information to you. So can't change it. It's too late. It's stuck. But we got to follow the rules so that we're all speaking the same language. So yep, Fg equals mg. It's always down. Someone did ask a really interesting question this morning. So when you get away from the Earth, this force will change. You can take G is 9.8 only on Earth's surface. If you get 50 kilometers away from the Earth, you get up near the space station and stuff like that, it's going to be smaller. You keep going, it gets smaller, 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 smaller. Someone asked an interesting question about inside the Earth, and that's really interesting. At the center of the Earth, the force of gravity is 0 because you're getting pulled in every single direction, so they all cancel out. And as you get closer to the Earth, it kind of decreases, but it's really, there'll be a slide on that eventually. Not that you need to know it, but it's just fun facts. All right. Okay, normally I would have you all solve this, but again, I want to move things along a little bit. This is just a confidence booster. You can try on your own. Mass of 70 kilograms. The gravitational force is just m times g. 70 times 9.8. Anytime I say the word magnitude, it means absolute value. Anytime you all see the word magnitude. And so the answer here, I don't even need to plug it in my calculator because there's only 2 numbers that are remotely possible. And newtons is the unit for force. So I'm not doing this in my head. 70 times 9.8. No, I'm not going to do that in my head. But it's bigger than 70, and the units are newtons. These are the skills you can use to quickly answer kind of questions. But again, that's one try on your own. This problem we already did today. That was the one we did before, so that's nothing new. So, great. Okay. Normal force I'll slow down now, and this is the one I want to spend some time talking about. Normal force doesn't have an equation. It is something you will need to find very often in problems, but there's not an equation. So I'm going to show you how to find it, and we're going to talk about that. Normal force, any surface. What is a surface? It's exactly what you want a surface to be. You know, that's a surface, a floor, an incline, a wall. Everything you think is a surface is probably a surface. If something is touching a surface, that surface is going to push back against it. You're standing on the ground pushes back up. You're sitting in your chair, the chair pushes back up. You lean on a wall, the wall pushes back against you. Otherwise, you'd fall through the wall. So, there's no equation for this. So how do you find it? Let's take an easy case, a flat surface. Gravity is going to be down. Normal force is always away from the surface. Always away from the surface. So if my surface is flat, it's away from that. If it's an incline, it's away from that incline. So directly away from it. If it's a wall, the normal force is away from the wall. Always away from the surface. The word normal in physics means perpendicular. And the way you can draw this, you're going to see this in physics too. So that's why I want to mention this skill. Super easy skill. If you're like, how do I draw this? Take a pencil, take anything. If you want to find the normal, just take the eraser and put it on that surface. And your pencil points in the direction of the normal. So if I want the normal of this table here, great. The top of the table, the normal is straight up. If I want the normal of the side of the surface, it points towards you. If I want it on the right side, it points to the right. And so if you have a curved surface, and you're like, man, just put your pencil there and it changes depending on where your pencil's located. Super, super easy way to find it. Makes it perpendicular to the surface. Okay, great. So how do I find the normal force? We do have to know the acceleration in the y direction. That is a requirement to find the normal force. So in this case, in this very specific case, I'm going to say that the AY equals 0. So how do I find the normal force? Well, the sum of forces in the y directions equals MAY. Okay? Fn plus negative Fg equals m times AY. If AY is 0, then Fn plus negative Fg equals 0. Move it over, and yay, the gravity equals the normal force. And so the normal force is equal to that. So that's what was going on right here. If their acceleration in the up and down direction is 0, then they equal each other. If the acceleration is not 0, they do not equal each other. And you have to do the math. So, I've got 5 minutes. I think I can at least do 1 or 2 of these. The question then immediately comes, what's a case where the acceleration is not 0? Like, how would that happen? You're in an elevator. You step into the elevator. You're on the first floor. You hit floor 3 and the elevator starts moving upwards. At the instant that elevator starts moving upwards, what is the sign of the acceleration? So I'll give you all a minute for this one. We should be able to get through these. I know we're kind of cramming at the end, but I want to make certain we have time on Monday and that these things are kind of ruminating in your mind before then. It's not a trick question. I could have given you all this as a kinematics in the kinematic step. All right, 20 seconds. All right, 5 seconds. 5, 4, 3, 2, 1. All right, so to answer this one, we're going to use our kinematics knowledge. You step in an elevator. What's your velocity before it starts moving? Great, it's 0. Then you start moving. Your velocity is up, positive or negative? Positive. If you go from 0 to positive, by definition, your acceleration is positive. Your velocity changed. Great, you got a positive acceleration. Great job. Fantastic. Like that's what we need to know, because now you're in an elevator. When it starts moving upwards, how does the normal force compare to the gravitational force? Let's find out what y'all think. This is the last one we'll kind of end on. Same thing, give you all a minute for this, and that should close us out nicely. All right, 30 seconds. Get something in. All right, 10 seconds. And 5, 4, 3, 2, 1. All right, so we draw a free body diagram. Normal force is up. Force of gravity is down. If my acceleration is up, if my acceleration is positive, which one's winning? The normal force is up. So my net force needs to be up to make that happen. So the normal force wins. And it's not equal to 0. They're not equal. It's bigger. When you jump, the normal force has to be bigger for you to leave the ground. That's another good example. All right, we'll continue with this next time and see how much it made sense, because the next one will be another elevator problem, but I'll save that for Tuesday. Yeah, have a good one, y'all. Good weekend, all that. See you around.